Magnitude is used to measure the brightness of different objects in the sky. Historically, it started with using just six numbers to classify different stars. But later we generalized this idea, so right now we can have any number for magnitude. First important point is magnitude works backward. So it means larger the number, dimmer the object. So in this case, magnitude 2 is dimmer than magnitude 1, or magnitude 4 is dimmer than magnitude 2. So in this class, 1 is the brightest class and 6 is the dimmest one. But right now we have other numbers. We have generalized to numbers in between, so we may have magnitude, for example, 1.7. That's perfectly alright. We can have magnitude 18. That's also alright. We can have negative numbers. For example, full moon is magnitude minus 12. So it's possible for a negative number. Sun is much brighter. For the sun, we have around magnitude minus 20. It's around 26, 27-ish. One important problem is what we see in the sky is apparent magnitude. So distance can change these numbers. So we may have a very bright star, but if we put this star far away, it will look like dimmer than nearby stars. So apparent magnitude is not a reliable number. This is what we see in the sky without taking into account the distance. We use little m for apparent magnitude, but it is similar scale and similar number. You may have 1, 2, 10, 10.5. In order to solve this problem, we use absolute magnitude. We use capital M for absolute magnitude. What we do for absolute magnitude, we put all the stars at the same distance, and this definition, it's 10 parsec. We imagine what we see in the sky if we put all those stars at 10 parsec. And this measured magnitude is absolute magnitude. And this is a reliable number because we suppose all stars are at the same distance. Now, we don't have any distance effect. We can compare different stars. For measurements, for comparison, we always have to use absolute magnitude, unless the stars are at the same distance. So for example, if we have a binary of stars, because two stars are approximately at the same distance, for this case, basically apparent magnitude and absolute magnitude will give similar results for some calculation. Okay, now let's talk about how we compare different stars. For example, this is just an example. Let's say we have two stars with absolute magnitudes 10 and 15. We use M1 and M2 for these two stars. So remember, a smaller number is brighter. So in this case, M1 is brighter and larger star. This star can produce much more energy compared to M2, or whatever name they have. For magnitude difference, we simply subtract two numbers. You can do either way, 10 minus 15 or 15 minus 10, but if you use positive numbers, keep them positive, it's easier for your next step. So 15 minus 10, larger number minus a smaller number, we always keep it positive. This is magnitude difference. So in this case, for this example, magnitude difference is 5. Your next calculation is energy factor. Energy factor is the ratio. It will tell you how much this star can produce energy compared to this star. How many times more energy can this star produce compared to this star? And energy factor is E is equal to 2.512 to the power of this magnitude difference. So you have magnitude difference. For this example, it's 5. Then for energy, we have 2.512 the power of 5. This is in power. This is not multiplication. So this number raised to this power, in this example, it will give you 100. Okay, now I have this number. What it means? This number means this star, smaller number in magnitude, produces 100 times more energy compared to this star. So in your manual it says energy per second, but be careful, this is not correct because this is actually the ratio. How many times more energy? So actually there is no unit for this number. Your next step is, okay, we said this star is brighter, this star is larger. How many times is larger? This is R, their size factor. And for the size factor, we simply take the square root of their energy. So we had, for this example, we had 100 in energy factor. A square root of 100, we have 10. And again, this is ratio. What it means this star is 10 times larger than this star. Okay? We have other formulas for individual stars, but be careful in your manual, whatever you do for comparison, we use 2 stars. Using 2 stars, we have 2 magnitudes, but we get 1 E for 2 stars, and we get 1 R for 2 stars. You can't do this calculation for this star and then repeat this calculation for the other star. You need reference number. We only can compare them. We can find their relative energy or relative size. Okay. What usually people are confused about is, I already told you we compare 2 stars with 2 magnitudes, 2 absolute magnitudes, and we don't do it for one single star. Okay, but there is one case you can use one single star. You can compare absolute magnitude and apparent magnitude. Okay, so this is for one star. We compare absolute magnitude, apparent magnitude. It is useful to find the distance because remember, absolute magnitude is a constant distance. We assume this star is in this specific 10 parsec, but apparent magnitude is wherever they are. Okay, so this is a constant number, but if we move this star farther away or closer, this number will change. Okay, so if we compare absolute magnitude and apparent magnitude for one star, we can calculate its distance. Okay, so this is for distance, not the size and energy. For distance, this is called distance module. For distance module, distance in parsec is 10 to this power. What is this power? This is simply the difference between apparent and absolute magnitude for one star divided by 5. Take that number, divide by 5 plus 1. Whatever you get, 10 to this power will give you distance in parsec. And you can check this number because if we put this star in 10 parsec, for 10 parsec, apparent magnitude and absolute magnitude are the same, so this difference will be 0. So 10 to 1, distance is 10 parsec. This is just sanity check. Let's talk about HR diagram. HR diagram is a way to measure brightness and temperature for different stars. For x-axis, we have temperature, sometimes you see spectral index or color index, they have the same meaning. What you need to know is, for temperature, we go backward again. This is hotter and this is cooler. So by moving away along axis, it gets cooler. Okay, this is x-axis. For y-axis, we have brightness. So faint and dim stars are down here, brighter, we go up there. What we expect to see is, we expect to see hot stars are brighter and cold stars are fainter. And this is our expectation. So in general, we expect to see stars are like this. Okay, so cooler, fainter, hotter, brighter. This is normal behavior. And this part is called main sequence. So main sequence is for typical star. For typical stars, burning hydrogen. But not all stars are here. So for normal stars, we expect to find them around the main sequence. But before they die, when they are out of hydrogen, they move to a different stage, which is called giant stage. Either red giant or blue giant. These are inflated supergiant stars. What happens? They move to this area. So this is for giants. So you can see giants are much brighter compared to similar temperature. So for example, let's take this temperature. For main sequence, we have this brightness, but for the same temperature for giants, we have this brightness, which is much higher. What's happening in this case? As I said, these are inflated stars. So having the same temperature, they also have much larger surface area. So because energy is proportional to the surface and they have larger surface area, they can produce much more energy. They can shine much more energy. So these are giants. Then they explode. After explosion, they turn to a dead star. But this dead star is losing energy and temperature. So they move to this part. And these are white dwarfs. Okay, so white dwarfs are hotter, but they are not very bright because actually they are dead stars. So these are three main regions of this HR diagram. So we have the main sequence, normal stars, we have giants, very bright stars but lower temperature, and we have white dwarfs, hot stars, but they can't produce any energy, they are not very bright. There is another important application for HR diagram. Let's say we have a big collection of stars and they are formed almost at the same time, like a globular cluster. Let's take one globular cluster, hundreds and thousands of stars, and they are born almost at the same time, but they have different sizes, different brightness, different temperature. So if we plot stars, globular cluster, we will end up with something like this. But what happens after few million years, they burn their resources. After a few billion years, they burn more resources and they should start to die. But which one dies first? Small stars or large stars? Because large stars consume much more energy compared to small stars, and compared to their size, they die soon. So if we have a sample of stars and they form at the same time, after a while you will see they die from this side. Okay? So by time, when they get older, this main sequence will start to shrink from this side. Okay? But remember, when they die, they move here. Okay? So after a while, you will see their main sequence has changed to something like this or something like this. What is important is we can use this turn-off point, read this number, and calculate their age. This is our reference diagram. In this reference diagram, we have HR, color index, which is temperature, and we have magnitude. But this is not one single cluster. There are multiple clusters. So for example, this is one cluster here. And this cluster is pretty young. You can see this cluster is around 10 to 8 years. Just 100 million years. So this one has shorter main sequence. You can see M11 is going like this, and it's older. This is 10 to 9 years, 1 billion years old. Moving down, we have NGC 752. It's much shorter, so it should be older. This is around 10 times 10 to 9 years old. This is 10 billion years old. And moving down, we have M67, and M67 is the shortest one in this case. You can see a lot of stars have died, they have moved here, and it's around 20 billion years. And you can see this is a strange number because, well, our universe is 14 billion years old, so we shouldn't have stars older than this number. So this is just an approximate number for different ages.